So electrochemistry is going to deal with two types of reactions. So one is called the oxidation, the other one called the reduction. And then these two reactions will happen together because if something got oxidized, that means actually its interacting partner got reduced. So the oxidation reduction reaction happens simultaneously. Previously, we actually talked about many different reactions. In chapter 13 and 14, we talk about the acid-base reaction. So those reactions involve the transfer of protons. In chapter 15, we talk about the reaction that involve the formation of the precipitates. In chapter 17 here, we are going to talk about so-called the oxidation reduction reaction, which is going to specifically talk about the transfer of electrons in your chemical equations. So again, the redox reactions is the reaction that involves the transfer of electrons. In this chapter, every time we see equations, you will always need to actually see how the electrons flow from one species to another. We are going to get very familiar with these things called the oxidation reaction. So when you see things called the oxidation reaction, it means actually a chemical reaction in which a substance loses electrons. So less species, if it lose electrons, then less species undergo a oxidation reaction. On the other hand, if in a chemical reaction, if a substance gains electrons, then we call that substance is undergo a reduction reaction. Just a highlight here, okay? If a substance lost electrons, is undergo a oxidation reaction. If a substance gain electrons, is undergo a reduction reaction. So another thing that is going to be very confusing is that you are going to hear this term called the oxidant or reductant or oxidation reagent or reduction reagent. This is actually the opposite of the oxidation and the reduction. Okay, so we're going to talk about a very confusing term here. So if you have a substance that lost electrons, that means actually it's undergo a oxidation reaction. So it lost electrons. It's going to give electrons to its interacting partner. This species, because it's giving electrons to the interacting partner, therefore it's going to reduce the interacting partner. So this species is so-called the reducing agent. On the other hand, if you have a substance that's going to gain electrons from your interacting partner, so in other words, you oxidize your interacting partner. So this kind of reagent, we call it oxidation agent, or sometimes you'll hear this thing called the oxidant. Okay, on the top is actually the reductant. In other words, if I bring up these two things up, okay, then it's basically a substance that lost electrons. It's undergo a oxidation reaction, right? But it can serve as a reductant, okay? And then if the species is gaining electrons, it's undergo a reduction reaction, but it can serve as a oxidant. I always use these abbreviations to help me to memorize the relationship. So I would suggest you do the same. So LOR, right? Lost electrons undergo oxidation reaction. It can serve as a reductant. Okay. After a couple slides, you will see another letter pop up. If you go to the electrochemical cells, this oxidation reaction will always happen at the anode. So in the end, you are going to use LORA. You tie all these things together so that you don't get confused. And then the other one is actually the gain electrons undergo reduction reactions can serve as an oxidant, and it's always happen at the cathode. Okay, so this A is for the anode, C is for the cathode. So the way I memorize all these things is actually using LORA and GROC. Okay, so that I can tie all these things together. So you're going to hear this LoRa G-Rock term a lot in the subsequent slides. So in order to figure out how the electron was flowing from one species to another, one very, very important thing is actually to know how to calculate the oxidation number of an atom. This is actually the most fundamental things that you want to master. The oxidation number can either be positive, 0, or negative. So the way you figure out the oxidation number of any atom typically follows the 5 rules we highlight here. So the rule number 1 is that if you see a substance or chemical formula existing in its natural form, then the oxidation number of that species is 0. For example, sodium existing in the solid form. So you can see you don't see any charges go with it first. Sodium is actually naturally existing in the solid form. So in this case, the oxidation number of your sodium will be 0. The same thing applies to your silver, mercury, oxygen, and hydrogen. They are all existing in their nature existing form. Therefore, the oxidation number of those atoms is 0. That's rule number 1. Rule number 2, if today you have your atom existing in the charged form, then its oxidation number is going to equal to the charge it carries. For example, sodium plus. So you can see here it's actually a charged species now. The things I gave you in the beginning, all the things is neutral, right? You don't see the charge go with it. But right now it's actually a sodium plus. That means actually right now the sodium, its oxidation number is 1. Chloride minus, that means the oxidation number of your chloride is -1. And this is the same. So Fe now carries +2, F minus carry -1. So if it's just a single atom with a charge on the top right corner, then its oxidation number will be the same as the charge it carries. So that's actually rule number 2. Rule number 3 and rule number 4 is actually things you are going to see very often. One is actually about the oxygen, the other one is actually about the hydrogen. If today you see a chemical formula carries oxygen, for example, NGO here, or SO2, SO3, CO, CO2, all these species, the oxidation number of your oxygen will be -2. Every time you see a compound or molecule where the chemical formula carries the oxygen, the oxidation number of the oxygen will always be -2. There's actually only one exception, which is if you have peroxides, then the oxidation number of your oxygen will be -1. The situation that you're going to have peroxides, this will only happen when you have H2O2 or your oxygen is actually from a compound with 1A group. Very important things that you need to actually know. Rule number 4, if you see a hydrogen inside a chemical formula, then the hydrogen will always carry +1. For example, HCl, NH3, H2O, CH4, all the H inside those compounds, it carries +1 charge. And then the exceptions of H is that when the H is forming a compound with 1A group, again, it's actually with 1A group, then you are going to have a oxidation number of -1. So the exception is always related to your 1A group, okay? Because 1A group always carries +1 if they form a compound. So 1A group is always carries +1 oxidation number when they form a compound. Another thing you will see a lot, even though I did not put it here, But I want to mention to you, if you look at the halide group, if they form a compound, they always carries -1. So I would suggest that you also put this 2 in here. So the very last rule to determine your oxidation number is that if you have a compound that did not carry charges, for example, your H2O did not carry any charges, but your Cr O4 2-, it carries -2 charges. So H2O is actually neutral, but your CrO4 2-, it carries -2 charge, right? So the very important concept is that if it is neutral, then the oxidation number sum of every atoms need to equals to 0 if it is neutral. That means actually the oxidation number of your H multiplied by 2 plus the oxidation number of your O, it should equal 0 for your H2O. But if it is like the things below, it carries -2, right? Then the oxidation number of your chromium plus 4 oxidation number of your O, you will need to equals to the charges it carries. If you see a molecule, you don't see it carry any charges, then the oxidation number sum of all atoms need to equals to 0. Otherwise, the oxidation number sum of all atoms need to equals to the charges that molecule carries. That's all the rules you need to know to calculate the oxidation of an atom inside a molecule. So let's do some practice here. In the next slide, you can see it asks you to calculate the oxidation number for carbon in CO2. First thing you need to actually make the judge is actually, is this neutral or charged species? Neutral, right? It doesn't carry any charges on the top. If you see charges, it will always show up at the top right corner here. Okay, so it doesn't show anything, means it's a neutral species. So since it is a neutral species, that means if you sum up all the oxidation numbers of all atoms, it has to equals to 0. So here you need to use your rule number 3, right? We know if you see the oxygens in a compounds, it always carries -2 charges. And then you have 2 of that oxygen atoms. And you want to figure out the oxidation numbers of your carbon. So the oxidation number of your carbon plus 2 times -2, it has to equals to 0. Therefore, you know the oxidation number of your carbon will be simply equals to +4. So that's how you actually figure out the oxidation number of a specific atoms inside a chemical formula. So let's do one more practice. H3PO4. So is this neutral or charged species? Neutral, right? You don't see any charges on the top right corner, right? So it's neutral. So that you know, the sum of oxidation numbers of all atoms need to equals to 0. So here we should know that if you have a compound with hydrogen shows up, you know it's going to carry +1 charges. And you have 3 of it, therefore you know there's actually 3 times +1. Phosphine, you don't know the oxidation number yet. That's the things you want to calculate. For the oxygen, you have 4 of them, you know oxygen always carries -2. So all these things are going to equals to 0. Therefore, you know this is going to equals to +5. ClO3 minus. Is this neutral or charged species? Charge, right? So what's this charge? -1, right? So let you know, you want to calculate the oxidation number of your chlorine. And then you have 3 oxygen, which each of them contribute a -2 oxidation number, right? And this whole thing need to equals to -1. Therefore, you know your chloride is going to have an oxidation number of +5. So the very last example we're going to give here is actually your S2O3 2-. So it's -2 charge. So you know You want to figure out the oxidation number of your sulfur, but you have 2 of them. Therefore, you multiply 2 in front of sulfur. Plus 3 times -2, that's going to equals to -2. Therefore, you can actually know that 2s is going to equals to 6 minus 2, which is equals to 4. Therefore, you know your S is going to be +2 charged. Okay, so its oxidation number of your sulfur will be +2.